Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all of you. So today we discuss about the tutorial 6, okay, for the sensor and transducer. Alright, so you can refer to the tutorial. Right, so let's go for the tutorial. Tutorial 6. First, I would like to share the question. Alright. Okay, you can see this one. Okay, so this is a tutorial 6, question number 1. Right. Okay. All right. So a sample of metal resistance versus temperature have following measured value lah. So they have a 1, 2, 3, 4, 5, 6, 7. Okay, they have 7 parameter. Okay, 7 value 1, 2, 3, 4, 5, 6, 7. Right. And then find the linear approximation of the resistance versus temperature between 60 to 90. Right. So the formula for linear approximation of the resistor is this is formula R of T, okay, equals to R T of naught, okay, multiply by 1 plus alpha, okay, delta T. Okay, so the RT is the approximation of the resistance. Okay, this one we want to find the linear approximation of the resistance. All right, and then okay, so the RT naught is a resistance at the temperature T naught. Okay, and then this one is the different okay, different on the okay, so on the T and T naught. Right. So we want to find this one. Want to find this one is the okay, from this one we can get the formula lah. Okay, from this equation. Okay, so this one, okay, since you can see this one, the center or the midpoint is the 75. Okay, is the 75 lah. Okay, at the midpoint is a 75. Okay, maybe you can use as the T naughts. Okay, so the R T naughts equals to 110.2 ohms. Okay, and then we can from this equation we can get the alpha lah. So alpha 1, okay, 112 point, okay, 0.2. So this one 1.2 is the 90. It's a 90 minus to 60. 0, okay, divide by 110.2, okay, 90 minus t. So the alpha is equals to 0. Okay, you can use your calculator to get this value. Okay, 0.01875. Okay, per okay. So this is the alpha. Right, and then we can get from this alpha we can get the relation lah. Okay, R of T equals to 110.2. Okay, 1 plus alpha is a 0.001875. Okay, multiplied by T minus 75. Okay, unit in ohms lah. Okay, so this is a equation for the linear approximation of the resistance. Alright, so this is a question number 1. Alright, so we assume a midpoint is the 75. Okay, so it's the RT naught here. This one is based on midpoint lah. Midpoint. Okay, right. So that's all the solution for question number 1. Next, we go for the question number 2. Okay, we go for the question number 2. I think based on the from the okay, from the this is equation number 2. Right, find the quadratic approximation of the resistance versus temperature for the data given in the example before this, 4.4 between 60 to 90. Yeah. All right. So this one based on the previous based on the question number one. Question number one. Right. So as we know, RT naught is equals to 100.2 ohms. Okay. So we want to find the alpha 1, alpha 2. So we want to find the alpha 1 and alpha 2. Okay. And then because of this one is the R on the 60, okay, on the 60 farad, okay. And then the Y is the 90. Right. So we can use the same formula based on the, for this is 112 point equals to 110.2 plus alpha 1. Okay, we assume this one alpha 1, 60 and 75 based on the first equation, plus alpha 2, 60 minus 70 power of 2. Okay, and then second equation 0.6. Okay, this is for 60, this is for 90 lah. Okay, 110. Okay, plus alpha 1, 90 minus 75, okay, plus alpha 2, 90 minus 75 power of 2. Right. So adding these two equations, right, to eliminate alpha 1, okay, alpha 1, so that we can solve the alpha 2 lah. All right. So the alpha 2 will be negative. Okay, you can solve this one lah, this eliminate of the alpha 1. 44. Okay, this is based on my calculation. Okay, you can check. Negative 44.36 multiplied by micro lah. Okay, micro, micro over, right, okay, power of 2. Okay, right. So that is the solution for question number 2. Okay, question number 2 lah. So there is the quadratic approximation of the resistance versus temperature. Right. So next we go for the question number 3. Okay, question number 3. All right. So this is question number 3 on the tutorial 4. Okay, from by the percentage of the prediction of the linear and quadratic approximation vary from the actual value at the 60 and 85 Fahrenheit. Okay, so so based on the first first equation. Okay, so actually the question number 1, 2, and number 3 will be have a relationship. So based on the question number, okay, number 1. Okay, so 60 Fahrenheit. Okay, this one 0.2. 1 plus alpha is 0.001875. Okay, so this one will be 60 lah, because this one is 60 minus 70. Okay, so the resistor will be 107.1 ohms. Okay, and then this is an error from the actual, okay, from the actual value of the 0.6 of 1 plus 1%, 1%. So at 85, okay, at 85 Fahrenheit, so we find the R, okay, 85 is 112.3 ohms. Okay, 85 Fahrenheit. Okay, and then which is the error is so this one will be error is 0.54%. Okay, this one will be okay, for 60 will be 1%, 1% error, 1% error. So the quadratic model from the example, okay, from the example, find the resistance to be, okay, so from from this one, the previous, okay, the previous alpha we get. So the R on the 60 Fahrenheit equals to 2, okay, plus 1, 0.001875, okay, 60 minus 75, okay, minus, okay, 4.36 multiplied by micro 60, okay, based on the second equation, based on the second equation, 5 power of 2. Okay, so you can use your calculator to get the answer will be 106.0 ohms. Okay, so there is a R in the 60 Fahrenheit. Okay, so this is a error is a zero error. Okay, so because of the endpoint, okay, the endpoints was one of those used to determine the constant, okay, for 85 Fahrenheit. So we find the 85 equals to, okay, for 85 equal to 111.8, which is the error will be plus 0.09%. Okay, and then so you can see clearly the quadratic approximation provide a much better approximation of the resistance versus temperature lah. Right, so there is a solution solution for question number 3. Okay, next we go for the question number 4. Okay, I will copy for the question number 4. Okay, question number 4 will be Rkd. All right, so question number 4, an Rkd has alpha naught 0.005 per Celsius. Okay, R equals to 500, and a dissipation constant of Pd equals to 30 milliwatt, okay, per Celsius at 20 Celsius, the degree Celsius. The Rkd is used in the bridge circuit such as that in figure 4.4, okay, which R1 equals to R2 equals to 500, and R3 is the variable resistor used to null the bridge. Okay, if the supply is the 10 volts and the Rkd is placed in the bed at 0 Celsius, okay, find the value of R3 to null the bridge. Okay, so this one. Okay, so the R equals to 500. Okay, 1 plus alpha will be given 0.005. Okay, so from 0 to 20. All right, so will be R equals to 450 ohms. Okay, this is a resistance at the 0 Celsius. Okay, so except for the effect of self-heating, so we will expect the bridge to null with the RT equals to 450 ohms also. Okay, so let's see what self-heating does to this problem. Okay, so first we have to find the power dissipated in the RTD form from the circuit. Assume the resistance still 450. The power will be, okay, so this is formula for power equals to I. Okay, so we have the VI and so on. Okay, so this another formula lah. Okay, another formula to calculate the voltage. Okay, so from this equation we can get the okay, and that we have to calculate the I equals to okay, this is voltage supply given here, right? 10 volts, and then this is a resistor to get the current. So the current will be 0.011 ampere, right? And then so we can substitute to this value lah. Okay, power equals to 0.011 power of 2 multiplied by 450. Okay, 450, and then use your calculator to get the power lah. So the power will be 0.05 watt. Okay, and then we get the temperature rise from the equation. Okay, from the equation, delta T equals to 0.054. Okay, divided by 0.03. Okay, 0.03 lah. And then the delta T equals to, use your calculator to get 1.8 degrees Celsius, 1.8 degrees Celsius. And thus, the RTD is not actual the bed temperature of the 0, okay, Celsius, but at the temperature of 1.8 Celsius, okay. So we must find the RTD resistance from the equation, the first equation. All right. So and this is the equation you have to remember lah. So 500, okay, by, okay, so the alpha will be given 0.05, right? So 1.8 minus 20, okay, okay, you can use your calculator, okay, 154.5 ohms. Right, so that's the R3 actually is the this is R3 lah, okay, equals to R3. So R3 equals to 454.5 ohms. Okay, this is for R3 lah, okay, the value for R3. Okay, so that is a solution, solution for question number 4. So next we can proceed for question number 5. Okay. All right. So this is question number 5. The thermistor is to monitor the room temperature. So it has a resistance of 3.5 kilo ohms at 20 degrees Celsius with a slope of negative 10% per Celsius. The dissipation constant is PD equals to 5 milliwatt per Celsius. It is proposed to use the thermistor in the divider of figure 4.5 to provide the voltage of the 5 volts at 20 degrees Celsius. Then the question, you have to evaluate the effect of self-heating. Okay. All right. So at 20 Celsius, the thermistor resistance will be 3.5. So this is given here, 3.5. Right. So we can calculate the from this one we can calculate the D lah. Okay, using the voltage divider rules. Okay, kilo ohms, right? 3.5 kilo ohms plus 3.5 kilo ohms, right? Multiplied by 10. Okay, so it works. Okay, actually the figure is something like this. Okay, so we have, okay, so this is our 10 volt here. So this is our 3.5 kilo ohms. Then this is VD. All right, so this is RTH. Okay, right. So now let us consider the effect of self-heating. So the power dissipation in the thermistor will given by, okay, this formula P equals to VR power of 2 RTH. Okay, so the V equals to 5 volts power of 2 and RTH is 3.5. Okay, 3.5 kilo ohms, and then the power will be dissipation. The power dissipation will be okay, you can use your calculator lah. So 7.1 milliwatt. Okay, and then the temperature rise of the thermistor can be found by equation. Okay, this equation lah. Delta T equals to P over PD. Okay, so and then this PD will be given, calculated this one, okay, 7.1 milliwatt, and PD is given, PD is a 5 milliwatt, okay, 5 milliwatts per Celsius, and then we can cancel the watt, so the value will be in Celsius, okay, the 1.2, sorry, 1.42 Celsius, degree Celsius. So this is the temperature rise of the thermistor. Okay, so but this means the thermistor resistance is really given by, right? So we have the RTH. Okay, so RTH, you can substitute the formula. Okay, minus 1.2, 0.1. Okay, and then multiply by 3.5 kilo ohms. Okay, so will be the RTH equals to 3 kilo ohms. Okay, 3 kilo ohms. And so the divider voltage is actually is the VD is 4.6 okay, 4.6, okay, 4.6, and the actual temperature of the environment is 20 degrees Celsius, okay, but the measurement indicate that this is not so. So clearly the system is unsatisfactory, right? So that is for solution for question number 5. Question number 5. Next, we can go for the question number, okay, number 6. Okay, so number 6 will be thermocouple. Okay, I clear this one. Right, so this is question number 6. The type K thermocouple is 75 Fahrenheit reference, produce a voltage of 35.56 milliwatt. What's the temperature? Okay, so this one actually we have a table lah. Okay, maybe we can refer the tables. Okay, maybe we have to refer the table for the K, type K thermocouple. So the reference temperature must be converted into Celsius. Okay, so this one, you can see this one. So this one in the Fahrenheit. So you have to convert into Celsius. Okay, the okay, you can so this one how to convert, you can check on the books, okay, the notes, okay, how to convert from Fahrenheit to Celsius. So this is formula, okay, divided by 9. So the temperature in the Celsius will be 23.5, because the table actually data will be on the Celsius. So this one given in the Fahrenheit, so that's why you have to change. Okay, you use the formula. So this formula will be given, okay, not already given in the notes. So you can use the formula to convert from the Fahrenheit to the Celsius. Okay, and then from this one, okay, we get the Celsius. We can use the okay, we can get from the table. So vote, okay, K 23.9 equals to 35. Okay, this one voltage 5.56 milliwatts. Okay, so now we need to determine the temperature. Okay, the voltage correction factor is determined using the zero Celsius table in interpolation formula. Okay, so the formula of interpolation you can refer to the, okay, this I will show some. Okay, you can refer to the notes or I will write here. So this is interpolation formula, measured, okay, lower plus BH minus this is higher, lower, divided by temperature, height, temperature lower, okay, temperature measured. Alright, so this is for voltage, okay, and then for temperature measured, TL plus TH minus TL divided by VH minus VL, okay, multiply by PM, PL. Okay, so this is interpolation formula. Okay, all right. So from this one, okay, we can refer the reference for the from 20 Celsius and 25 Celsius. So you can see K naught at 23.9 Celsius, 0.8 plus, okay, so 1 minus 0.8 divided by 25 minus, okay, this one you can refer to the table, table for K thermocouple. Make sure it's the correct type of the thermocouple. So if the J, so you have to refer J. Okay, if K, you have to refer the K table lah, right? But for example, like for the final exam or for normally will be given lah. Okay, will be given. Okay, the table will be given. So you have to refer the table lah. Okay, 23.9 minus by 20 lah. Okay, so the voltage is the 0.96 okay, millivolts. Since the reference is the greater than the table reference, so we would expect the table voltage to be larger lah for the same temperature. Thus, the correction is added to measure the voltage. Okay, so V Kd of T equals to 35.5. Okay, this one millivolts. Okay, plus we assume as a millivolt lah, plus 0.9. Okay, plus this one okay, so the answer will be 36.52 millivolts. Okay, and then from the table, okay, from the table of the K thermocouples, so this voltage, okay, this voltage lie between the okay, so you can refer to the table lah. Okay, this one okay, from this one 36.35 okay, milliwatt at, okay, you can refer. So this one you have to refer to table lah. Okay, 75 Celsius and 36.55 okay, millivolt, okay, at 880 Celsius. Okay, so we can so from the table, okay, we can get the value here, and then we can use the interpolation techniques. So 875 plus 800 plus 875, okay, 36.55 minus 36.35, okay, 36.52 minus, okay, 36.35. Okay, and so you can use your calculator to get the temperature. So the temperature will be 879.3 okay, Celsius. Okay. So this is the temperature. Okay, this is temperature for K thermocouple at the reference 75 Fahrenheit. Okay, the first step, make sure first you have to convert. Okay, we have to convert into Celsius. Okay, using this formula lah. Okay, this formula you can check on the notes. After you get the formula, okay, we have to use the interpolation. Okay, interpolation. Okay, so this is voltage, and then after that you have to add the voltage, this one. Okay, 35.56 plus 0.96, okay, to get the voltage here. And then from this one you have to refer to the table lah. Okay, question number 2, yeah, step number 2, you have to refer to the table So the table we have the range lah. Okay, the range for this one so between, okay, you can see so divide 2 between this one 35.55 and 35.55, okay, at this one 35, sorry, this is 0 35, okay, 35 that's why this one between 2 okay, this one maybe range here 36.52, okay, and then you can use the interpolation formula to get the temperature. So that is the solution for question number 6. Okay, so next, Okay. All right. So next we go for the LVDT. LVDT. All right. So an LVDT has the maximum core motion of the plus minus 1.5 cm with the linearity of plus minus 0.3% over that range. So the transfer function is 23.8 millivolt per mm. If used to track workpiece motion from negative 1.2 to 1.4 cm, so what is the expected output voltage? So what is the uncertainty in position determination due to non-linearity lah. So we have to question what is the expected output voltage, and then what is the uncertainty in position determination due to non-linearity lah. So okay, we go for the solution using the unknown transfer function. All right, so the output voltage can be easily found lah. All right. Okay, so V negative 1.2 cm, all right, goes to 23.8 millivolt per mm multiplied by 12, okay, milliampere, right? So equals to negative 285.6, okay, millivolt. Okay, and for V 1.4 cm equals to 23.8 millivolts per mm. This one mm, okay, multiplied by 14 mm. So to get that 333 point no, okay, 33.33 millivolts. Okay, so the linearity deviation show up the deviation of the transfer function, so that the transfer function has the uncertainty of okay, plus minus 0.003, okay, multiplied by 23.8 millivolt per mm, equals to plus minus 0.0714 millivolt per mm. Okay, so this means that the measure voltage Vm is in millivolts, so could be interpreted as the displacement that range from the okay Vms per 23.773 to Vm per 23.87 mm lah, which is the approximately plus minus 0.3 0.3% as expected. So that's it. If the sensor output was 33, okay, is this one is the 330 millivolts, which is the nominal is 1.4 cm. So the actual core position could be ranged from the okay plus minus lah, okay, from this one plus minus, okay, so we can use your calculator. That means from the range 1.40329 to 1.39506 cm lah. Okay, cm. This is 2. Okay, so this is the actual core position lah, okay, in this range lah, from 1.4 to 1.4 something to 1.39 something lah. Okay, this is the actual core position. Okay, next we go for the question number 8. Okay, question number 8. Contrast the resistance chain produced by 150 microamp per amp strain in the metal gauge with the gauge factor, okay, equals to 2.13 with the semiconductor with the Gauss factor is the negative 151. Okay, so the nominal resistance both is 120 ohms. Okay, so we can use the formula for measure the Gauss factor. The Gauss factor, okay, this formula you can refer to the notes lah. Okay, right, by straight. Okay, so first we have to calculate the this one, the delta R lah. So delta R equals to, okay, using this formula, formula 150, okay, multiplied by 113, okay, multiplied by 0.153. Okay, so the delta R equals to 0.038 ohm. Okay, and then for the semiconductor gauge, so the change is the delta R. Okay, you can use the same formula, but this one will be different lah. Okay, 151 multiplied by 0.15 negative 3. Okay, so the delta R equals to this one for A, this one for B lah. Okay, is the negative 2.72 ohms. Alright, so this is the solution, solution for question number 8 lah. Alright, so next next we go for the question number 9. Okay, question number 9. Okay, this is question number 9. Okay, so the figure, this one 5.2 shows the simple load cells consisting of the aluminium post of the 2.5 cm radius with the detector and compensation strain gauge. So the 120 ohms strain gauge are used in the bridge of the figure 5.16, which volt equal to 2 volts, okay, and R1 equals to R2 equals to RD equals to 120 ohms, and then the Gauss factor is a 2.13. Okay, so find the variation of bridge offset voltage for the load of 0 to 5000 lb. Okay, so we can find the strain of the 5000 lb loads, then the resulting change in the resistance, and from that, so the bridge offset voltage lah. So the first we have to change the force to the Newton. Okay, first we have to change the force to the so the this one in the Newton. So this one is the convert into Newton lah. So you can use your calculator. Okay, so 0.04 lb per Newton. Okay, so on the Newton will be, you can use your calculator, 22,240 Newton lah. Okay, in Newton. And then the cross sectional area of the pores is the A pi r squared. Okay, r squared. Okay, so pi is a, you can use your calculator lah. The pi is a 3.18. Okay, 3.14842 something lah. Okay, multiply by 0.025 meter per square. All right, so the answer will be 1.963 multiplied by negative 3 meter square. Okay, so this is area lah. Okay, the cross sectional area. Okay, from the table. Okay, so the modulus of the elasticity aluminum E. Okay, this one from the table, E equals to okay, this is E, this elasticity of the aluminum. 6.89 multiplied by 10 power of 3. Okay, sorry, this one is minus 3. Yeah, so this one minus 3. 10 of 10. Okay, 10 of 10. Sorry, so 10 of 10. Okay, from this from the equation, so we can find the we can find the strain. Okay, delta L per L was divided by EA. All right, so delta L per L. Okay, so the force will be 22 110. Okay, divided by our electricity. Then multiplied by sectional is 1.9 negative 3. Okay, so we can get the delta L per L equals to 1.644 multiplied by 10 negative power of negative 4. Okay, equals to we convert into the micro lah, so 164.4 micrometer. Okay, per meter. Right, so the relationship between the resistance, okay, and the strain is given by equation, okay, Gauss factor. Okay, so based on this equation, okay, Gauss factor equals to delta R per R divided by delta L per L. Right, so the resistance, we can get the resistance delta R per R equals to, okay, Gauss factor is the 2.13 multiplied by delta L per L is the 1.4. Okay, so here is the change of the resistance. So you can use your calculator to get this value. 3.5 2 multiplied by negative 4. Okay, and then because the R given R is the this one is a 120 ohms, then delta R equals to 0.04203 okay ohms. To get the bridge offset voltage, so we note that the post under compression and therefore the resistance will be decreased. All right, so with no strain, the bridge is now under the 5000 lb loads. The active gauge has resistance is the 119.958 ohms. Okay, 9595. This one 5, right? Thus the offset voltage of the bridge is equals to, okay, you can use this formula. Okay, delta V equals to multiplied by 120 divided by 20 plus 50 minus 2 multiplied by 120 158 120 minus 119.958. Okay, and then for this one, we get the value lah 1.725 by negative 4 volts. Okay, and then okay, convert into the micro 75 microvolts. Okay, as the force vary from the 0 to 5000 lb, so the offset voltage vary from the 0 to 175 microvolts. Okay, this one vary from 0 to okay to 175 microvolts. Right, so that's all for the tutorials. Okay, I'll just cover until the until the question number 9. Right, for the tutorial 6. All right, so I stop here. Okay, you can try at home. Okay, to check again. Is it my solution is correct or not? Okay. All right. So thank you very much. Okay. Assalamualaikum warahmatullahi wabarakatuh.